Sorry that office hours wasn't available yesterday. The internet in Davis was down the whole day. Um, so I might try and offer office hours uh, later on this week. And I'll post that on Canvas. So we'll have a makeup. It came to my attention that not everyone is aware. Um, let me just show you. So on Canvas, oops. So on Canvas, I actually make notes for the course. And so you can find those posted under the files. Let me just pull an example up so you guys can see. Because it's difficult to take notes and sort of follow along at the same time with some of the coding materials. I do prepare class notes on the materials that we cover. So for example, this is notes from last class, looking at variance and bias, trade-off, and then looking at some of the examples. So most of the stuff that we cover, and maybe a little bit more detail on certain materials, those are all available in the files on Canvas, as well as the code notes. So make sure to use that as a resource as needed. All right. We are going to start off today on the whiteboard. Okay, so today we'll be talking about looking at causality. So as most folks know, correlation does not equal causation. And so this is probably one of the more common misconceptions. And actually, even though many people know about this, oftentimes when we talk about interpreting outcomes from your regression results, people will often still think of the effect of X on Y and interpret it sort of causally, even though that's not the case. I should briefly mention that the field of regression is fairly broad, and when we think about sort of more statistics or machine learning, such as some of the techniques we were learning last time with regularization, so both ridge regression and lasso regression, a lot of the techniques are more concerned with getting your prediction as good as possible. So thinking about, if I have a set of X's, how can I calibrate my model to get Y's to predict out a sample as best as possible? But when you induce changes in X directly, they may not necessarily lead to the same outcomes in Y as you're measuring. It's more of, as I observe X's, I can predict Y. And so that's a pretty important distinction, because those types of models will not necessarily get you causal feedback. Okay, and so the difference, so correlation is a relationship between two variables, whereas causation is when one event is the result of the occurrence of other events. Okay, and so to talk about this concept today, we are going to learn the basics of what is known as a directed acyclic graph. So this is a finite directed graph with no directed cycles, so no loops. This is also known as a DAG, D-A-G. And so we're going to use this to demonstrate direct causes, or use them for what are known as graphical causal models. Okay, so I think if we just dive straight into the example, this will be made a little bit more clear. Okay, so let's think about heart diseases. So if we suppose this is the outcome of interest, I will draw out a graphical causal model. So it's a sort of network diagram. So one of the things that can lead to heart disease is inflammatory immune response, so note that in these causal models, in these directed acyclic graphs, when you go x to y, we denote this arrow as a direct causal relationship. So you know that essentially, as I change x independent of everything else, it leads to changes in y. Okay. So gum disease can lead to inflammatory immune response, and gum disease is a direct function of frequency of brushing teeth. Okay, so that can be sort of one side of our causal model. And so from this, if you establish this relationship and you have the data and you are able to measure sort of frequency of brushing your teeth, this can sort of directly relate to heart disease. And so let me just quickly talk about some nomenclature for the graphical causal model. So actually, let me clear this circle. when we talk about the network, the things downstream are children and the things upstream are parents. And as you go down, it's kind of intuitively obvious. So you have your descendants and your ancestors. Just a bit of nomenclature. We probably won't talk about it that much in terms of ancestors and descendants and parents and children. But that's how they're often referred to. Okay, so in this causal model, let's introduce a couple other things. So health, consciousness. So the more healthy you are, then the more frequently you might be brushing your teeth. And the healthier you are, maybe your frequency of exercise will be affected. And this may affect your heart disease in some way. And maybe this will also affect, let's say, amount of fat and red meat in diet. Okay. So this is a sort of full model diagram for a graphical causal model. And one of the interesting things here is actually, now that I've introduced these sort of other factors, suppose that I have data about frequency of brushing your teeth. Okay. In this model, unlike before, I can no longer tell what the causal relationship is between the frequency of brushing your teeth and heart disease. So suppose I can observe, a bunch of people who have different levels of heart disease and have different frequencies of brushing their teeth. In the previous model, you may be able to elicit the sort of causal relationship, right, by understanding, differences in the amount of people brushing their teeth related to differences in heart disease. And so this might be, a simple linear regression where your y is your incidence of heart disease and your x's are frequency of brushing your teeth. And had the model been sort of confined to just our initial part, so cutting out all of this, then you are able to make some conclusion about the relationship, the causal relationship between frequency of brushing your teeth and frequency of heart disease. But that's actually no longer the case once we introduce the full model. And so why is that? If I brush my teeth more frequently and I observe the heart disease, well, you may see a decrease in heart disease, but that may actually be because of a person who is generally health conscious may also be exercising more often and may also be, eating less amount of meat and fat. And so you can now no longer be sure about whether or not it's the actual brushing of the teeth or it's because they're generally health conscious and people who brush their teeth a lot tend to also exercise more and have a healthier diet. And so if you were just to change their frequency of brushing their teeth, you may not observe the sort of causal difference in heart disease because it's related to the other variables. So essentially, what you want to do is to be able to remove that relationship, or to essentially to make this independent from your health consciousness. So if you were, for example, able to observe, twins who have the same sort of diet and exercise and frequency of brushing their teeth, and everything else about their lifestyle is the same, and you can just change the frequency of brushing the teeth without changing the frequency of exercise or their diet, in this case, then you'd be able to sort of re-observe the relationship between the teeth brushing and heart disease without it getting confounded by other sort of parallel factors. Okay. And so this process is known as conditioning. So we'll talk about this sort of in a theoretical aspect, and then we'll think about how that theory has been sort of explored to be able to conduct sort of causal relationship and investigating those causal relationships in practice. So if I think about x going to y, you may have some sort of probability of x. So this would be your p of x and your p of y. And so this may be, on the left, the distribution of possible x values. And on the right would be your distribution of y values. And understanding the relationship between your x and the y is where you may actually affect this distribution. So suppose I were to select a set of x's here. So this might be a set of xa. So there's always a corresponding x and a y. And in fact, if I condition y on x equal to xa, then you may actually have a really different distribution. So even though y looks like the above, you may end up with something that looks maybe like this. So this is getting at understanding the relationship between your x and your y's. And so as you change from xa to xb, which corresponds to some change in your y given x, this is what we would call a causal effect. So hopefully you've seen from the previous example, or the first example, so one of the nice things we can take advantage of is that causal inference flows only one direction. So when we talk about x going to y, we know that x causes y, but y doesn't cause x. So this is one direction in direction of arrows. But we actually know that statistical information flows in either way. Which allows us to, so we can infer an effect from its causes, but also we can infer causes from their effect. Okay. So to give a general sense of what our issue is, the general problem is something like this. We have our x, and we have our y, and then we have unknown variables. So if I were to want to think about the causal relationship between my x and my y, and I just measure my x and my y, or I just have data on my x and my y, you are always worried about having this confounding variable. So u confounds effect of x on y. So the case before that we had was our x is brushing your teeth and our y is heart disease, and then the u would be something like the general health consciousness of the individual. And so in econometrics, we talk about something called identification. And so this is the strategy to remove the confounding effect and determine the causal effect. Okay, so let's talk about different strategies to do this. In the first example, one of the ways you can do this is to control for all of your variables on the side. And so this would be something like if I were to be able to observe, if I were to be able to observe not only the frequency of brushing your teeth, but also the frequency of exercise and the diet outcomes. And so you are now able to condition your model not only on the frequency of brushing your teeth, but you control for how exercise and diet will affect your heart disease and sort of correspondingly health consciousness. So that's one strategy, and that is known as backdoor and so this would be blocking all indirect paths from X to Y. So that is a valid strategy, but it can be, so I think this one in particular is a lot more rare in practice. And that is because it's difficult to block all the paths. So yes, we get exercise and diet, but you could probably come up with a dozen more examples of how health consciousness may affect heart disease, not through exercise and not through diet, right? It could be, things related to like mental health, for example. And so you would literally need to be able to reasonably block off all of those indirect paths and justify being able to, or justify sort of blocking all the paths to a variable like health consciousness. So generally, it's a little bit more difficult to prove. Okay, I see a question. With data available for each variable, how can we come up with the graph in the first place? By hypotheses. Yeah, exactly. So you can generate the graphical causal model based off of your initial hypotheses, and then you can test relationships between variables to make sure you've got everything sort of in the right place. Yeah, so I'm skipping over a lot of details here, and this actually, I will say this has been one of the more historically difficult parts of the class to teach, because getting into the network diagrams and proving how they work gets into a lot more statistical theory than typically I am able to cover in this class. And so if you want to learn more about, DAGs and graphical causal models, I would probably have to point you to more advanced statistical classes. But that having been said, I think the concept of the graph network diagrams can help with understanding why it is we do, or why it is we take certain approaches. And so I guess I'll leave it at that. Unfortunately, we won't cover how to robustly demonstrate that like the diagram is right. More that, if that's what you came up with in your hypotheses, or you're given sort of certain relationships, it'll give you a sort of clear idea about how to approach solving issues of causality. Okay. So that's the first technique, is through this backdoor method. There's another method, which is also relatively rare, called the front door. So all direct paths from x to y pass through a mediator variable. And so this would look something like this. Okay, and so if you have information about the mediator variable, you can condition on that variable in order to understand, in order basically to break the relationship between your confounding effects on X. So you can't have any direct relationship between. Let me change the color actually so that not confusing. So you can't have any relationship between your confounding variable and your mediator variable, which can be difficult to do sometimes. And so thinking back to our first example, you may think of maybe something like inflammatory immune response as a mediator variable, but that may be not entirely clear in this case, because you may actually have some relationship with your confounding variables. And so this can also be somewhat tricky to do. Okay. And the last technique, which is the most common and the one we'll spend the sort of rest of the time looking at, is known as instrumental variable. Oops. So this is something which affects X and Y, but only through okay. Let me rewrite this. So it affects X and affects Y only through X. So this would be something like, if I have my X and my Y and my confounding variable, the instrumental variable would look something like this. And so your instrumental variable is something which is affecting the variable of interest that you want to measure the causal relationship between X and Y, but is not in any way related to any of the confounding variables. So something like this so this is no good, and you can't have something like this. This is also no good. So it can definitely be pretty tricky to come up with an instrument. But if you are able to come up with an instrumental variable that isn't affected by, doesn't relate to your confounding variables at all, then what you can see is that your instrumental variable will affect your X in some way. And the way in which that affects your X is not at all related to any of your confounding factors, which means that that marginal change in X is leading to some observable outcome in Y. Okay, and so if I think back to this example, we are, again, we're sort of really mainly concerned with frequency of brushing teeth as it relates to heart disease. And so what might an instrumental variable be? I won't put anyone on the spot here, but sort of think to yourself, what might affect how frequently you brush your teeth, but isn't related to your health consciousness. And so one that comes to mind, sort of off the top of my head, is suppose it's related to your dentist's orders. Okay, and so the dentist, if you are able to measure this somehow, right, some kind of factor in terms of them making a suggestion that you need to brush your teeth more often. And in this case, suppose you have like some panel data across a whole bunch of individuals, and you observe some subset of individuals where you can observe that their dentist told them to brush their teeth more often. And then you see a whole bunch of individuals where the dentist didn't say anything. So if you measure the difference in how frequently the person brushes their teeth, and you can observe some effect of the dentist suggesting that they brush their teeth, if you go all the way down to the outcomes about heart disease, if you've got a big enough sample, say, of the population, then essentially, if you've captured sort of the heterogeneity in people's frequency of exercise and diet, as well as the difference in the frequency of how often they brush their teeth, you can attribute changes in the heart disease outcome based on the differences in frequency of brushing their teeth directly related just to the dentist giving those orders and not related to the health consciousness outcomes. And so essentially, by introducing dentist orders here as an instrumental variable, you are effectively getting or controlling for that relationship. Okay. So instruments are a common tool to get at causality. But I should mention some caveats about instruments that I think are not discussed as often. So okay, well, so before I go there, the selection of an instrument can be somewhat more of an art than a science. Okay, so there are ways of testing how good an instrument is, but oftentimes you'll find, so if you go into economic literature, or if you watch, an econ seminar or something where someone has identified, an instrumental variable, a lot of the justification for the instrument, you'll hear, oftentimes it's all about kind of qualitatively justifying the relationship between a lot of these variables. And so here, we haven't talked at all, right, about any of the numbers or coefficients or any sort of statistical tests about the relationship between these variables. And that's often sort of how it goes. When we talk about a valid instrument, it's all about justifying the fact that dentist orders isn't related to frequency of exercise, and the diet that you have. And in fact, most, and maybe this is a mischaracterization or generalization, but I find that most econ papers that do this type of analysis, there is oftentimes a lot of time and effort dedicated to saying that dentist orders isn't related to exercise and isn't related to diet, and that's because if your instrumental variable is related to your confounding variable in any way, that invalidates the instrument. And so you need to justify it, both qualitatively and quantitatively. But the part that gets glossed over a lot in these discussions is that, in the way in which we conduct an instrumental variable regression, which I'll show in a little bit, can actually lead to lots of issues in the regression that are unrelated to the fact that an instrument is good. So even if an instrument is good / valid, if it is weak, then it may lead to a lot of noise. So not so good for predicting. Okay, so what does that mean? So what does it mean that it's a weak instrument? So this example that I gave for this example that we've been talking about with the dentist orders, that may be a really good and really valid instrument if we can discuss and look at the relationship between dentist orders and, say, your diet and exercise. And we may find that it's pretty much independent of that, right? That the diet and exercise related to the frequency of your brushing your teeth, it can be a reasonable assumption that we have a valid instrument because the dentist is giving that advice independent of your confounding variables. But you may actually find that there is a fairly weak relationship between how a doctor, how often how frequently you brush your teeth and your dentist's orders. So maybe it's the case that a lot of people just don't listen to their dentist. So even though it's a good instrument, it's what we would refer to as a weak instrument. And that may actually lead to a lot of uncertainty and a lot of noise, right? Because now your sort of error about your relationship between the dentist and the brushing of teeth is really high, which will propagate your errors for brushing your teeth related to heart disease. And so one thing that you probably won't hear about so often is that so sometimes sometimes predictive outcomes in a biased OLS are better than unbiased, high variance instrument. So what this means is that if I am more concerned with predictive ability rather than the causal relationship, it can definitely be the case, and I've seen, actually more often than not, I've seen this. So in this exercise, if I were just to regress teeth brushing versus heart disease, as opposed to doing an instrumental variable regression where I do, where I first look at dentist orders related to brushing your teeth and then brushing your teeth related to heart disease outcomes, your predictions may actually be better in the first case, even though we know it's biased, because you've got this health consciousness thing going on. And so that's going to be one of the drawbacks here, is that you have a lot more uncertainty. And what effectively that means is oftentimes like your variables become less statistically significant or become statistically insignificant as you introduce instrumental variable into your regression. So, when we think about when you think about trying to do an approach like this, you really want to think carefully about what your goal is, right? Are you mainly interested in understanding sort of the relationship between your changing your outcome X on Y, which may be really relevant for example, like understanding the effect of like a policy mechanism. That might be something where you do really want to nail down the causal relationship and make inferences on that. versus if I just care about getting the most accurate outcome possible, you may want to stay away from doing some of the more robust causal analysis because of the drawbacks that it's going to lead to in terms of your predictions. Okay. Why don't we take a quick break? Let's reconvene at about 11 o'clock. And then we'll continue on and I'll show some application of the instrumental variable in practice. All right, let's continue on. If there aren't any questions, feel free to ask
Hey,
or,
Alan.
yeah.
Yeah, I have a quick clarifying question.
Mm-hmm.
When an instrument is weak, like in the example you did, would that mean that there wasn't much of a relationship between dentist sorters and the frequency of brushing your teeth?
Yeah, exactly.
Okay.
Yeah, so weak instruments basically mean the relationship, yeah, between your IV and your explanatory variable of interest are kind of weak, or yeah, not uh, they're probably a little bit more uncertain. That's what I would say.
Okay, thanks.
Mhm. Any other questions? Confusions? Okay. Everyone's all good. Let's talk about an example, a different example, which we're going to implement in our studio. So here we're going to look at BMI. So this is body mass index. And we've got a whole bunch of variables that go into this. Gender, pregnancy, education, and smoker. So suppose I want to know the causal effect of smoking on BMI. You might imagine that if I were just to run this regression, that you probably wouldn't be getting necessarily a good relationship, a causal relationship or measurement of causal relationship. Why? Because again, we've got some confounding relationships here, and so you know, this could actually be similar to the health consciousness type thing, right? And so smoking may very likely be related in some way to your education level, probably how pregnant or whether or not you're pregnant, um, gender, age, and also income. So you've got kind of a really terrible causal diagram here in which your smoking is related to all of these things. And so here I think it's a pretty easy example of why it would be really difficult to do a backdoor, because you'd need to essentially cut off the relationship between all of these variables, and any unobserved ones that aren't even here aren't included. So that would be something like where your confounding variable is related directly to BMI. So all of that would be an issue. And so we want some variable z to be able to control for whether or not the person is a smoker and is unrelated to all of these other things. Okay, so how do you actually run an instrumental variable regression? So in our ordinary least squares, we do something like y is equal to beta x plus epsilon. So in instrumental variable, there's a technique called 2SLS, which stands for two-stage least squares. So the way this works is you first measure the relationship between your instruments and the variable of interest. Okay. And so these Greek symbols are just alternative coefficients that I'm specifying. So this in itself is essentially two sets of regression. I'm going to regress first my x on z, and similar with an OLS where you can have your y hat is equal to your beta hat x, you can have your x hat equal to delta hat z. So this is first stage. And then in our second stage, instead of y equals beta x like before, you're going to use your predicted x like so. And so what you're doing here is you are controlling for differences in your x related to all of your confounding variables, and you're only caring about how your x varies as it relates to your instrumental variable. So if I were to write this out again, so BMI, so these are a bunch of your U's, and then you have your smoker. We want an IV here. So let me come up with a couple different instrumental variables. Cigarette tax, unemployment, and separated / divorce. So these are potential IVs. And you guys can think to yourself about which would be good instruments. And just to be clear, I mean, when I say good versus bad instrument, that's more about the validity of the instrument. And when I say strong versus weak, that's more of talking about the relationship between your instrument and your causal variable. So we'll call this CT. So the way this would work would be something like X, oops, let me, smoker is equal to delta cigarette tax. And then once you estimate, so estimate coefficient, this is first stage. Then in the second stage, we say BMI is equal to, actually here I have to, let me just plus delta of all of my other variables. I shouldn't write U because that's going to be confused with the unobserved. So this would be plus delta income plus delta age and so on and so forth. But we only care about we only care about the one of the causal variable. And then in the second stage, what we're going to have is beta of cigarette tax predicted. And then everything else will be the same. So beta 2 income plus beta 3 age, and so on and so forth. So in your first stage, you still control for how these things are related, all your other variables, and that can actually be one way of observing, or one quantitative way of observing whether or not your instrumental variable choice was a good one, because really a lot of these relationships should be basically really small or sort of non-existent, right? Because the whole point is that your confounding variables are not related to your instrumental variable.
Alan, can I ask you a question?
Yeah.
So in your second stage model, BMI is equal to beta 1 of cigarette tax.
Oh, whoops.
However,
Sorry. Wait. This should be like this. Yeah, so you predict the smoker from your first stage. You plug everything in, and then you observe changes in smoker from your cigarette tax.
I see. So is smoker hat equal to the equation from the first stage?
Yeah, so think about in the regression model, you have y hat equals beta hat x, right? So you predict your, you calibrate your model, you figure out what your coefficients are, and then you do a prediction, which are your y hats, and you can predict based off of the values that are given. It's the same thing here, except you're doing it just for the first stage where you're predicting what the smoker is, and then you use those predictions in your second stage,
Okay,
as
that
opposed
makes
to the
sense.
actual value of the smoker.
Okay, thank you.
So let's jump into R, and we can take a look at how to implement this. Okay. One moment. Need to make sure that I have the, oops, didn't move my data set over to the right folder, so give me 1 second. Okay. So I'm going to load in some data. Uh-oh. I need to navigate to the right working directory. All right, one more try. So let's take a look at this data. Summary, BMI data. Okay, so let's look at the columns. State FIPS code. So this basically tells you, I believe these are just state codes. Then you've got year of the data, income, income squared, age squared, whether or not they're female, whether or not they're pregnant, level of education, whether or not they're a smoker, whether or not they're separated or divorced, whether or not they're unemployed, their BMI, and then the cigarette tax in the area where they're living. Okay. So the first example that I'm going to look at is our standard linear regression ordinary least squares. So this is just a linear model where I'm regressing BMI, body mass index, on income squared, age squared, whether or not they're female, whether or not they're pregnant, their level of education, and then whether or not they smoke. So let's go ahead and look at this. Okay, one moment. So in this case, hang on, I'm getting a slightly different answer. Oh, no, okay, we're good. We're on track. All right, so we can interpret this, right? And so the relationship that we're specifically interested in is the outcome on your BMI from whether or not you smoke. So it looks like if you are a smoker, then on average, your BMI is 2.9 or 0.29 higher on average. And so that's what we observe in the data. But now there's this question of, if you smoke, right, how will that change your BMI? And so we're really interested in understanding the causal relationship between smoking and BMI. But we know that probably the fact that you smoke is somewhat related or confounded by, or the relationship between smoking and BMI is probably confounded by some other variables that either you're not controlling for or are related to other explanatory variables. And so we want to be able to isolate that. So actually, I think I kind of skipped over one thing I wanted to discuss. If I go back to my whiteboard, oh man, apparently all of the notes disappeared. That's all right. The three things that we wanted to consider as IVs were unemployment, divorced / separated, and cigarette tax. So which of these might we consider to be a good instrument versus a bad instrument? Well, so unemployment, let's think about unemployment as it relates to the other explanatory variables. So this could be likely related to your income, and maybe it's also related to your age in some way. And so, you know, maybe younger or older people are more or less likely to be unemployed, right? And so because you've got some relationship there, unemployment is probably not a great instrument. Divorced, whether or not you're divorced or separated, that could be related also to income, age, right? If you're younger and you just got married, it's less likely that you're divorced, right? And so there is some kind of direct relationship between age and being divorced and separated. Could also be related to whether or not you're pregnant. Could also be related to your education. So another example of an instrument where the justification for the instrument is probably not very strong. Meanwhile, the cigarette tax, that probably is something that is a good instrument, right? Because the fact that there is a cigarette tax is probably unlikely to be related to, you know, you as an individual having, you know, more or less income, being older or younger. The decision to make or the decision or indifference between cigarette taxes at the state level is likely not related to any of these individual attributes. And so we might say, okay, this is actually a good instrument. And so these are the things that that you should be considering as you select variables to instrument. All right. So let's take a look at how to do this manually. Two-stage least squares. So we'll do an example of a bad instrument first. Okay. So let's walk through this code. As I was mentioning before, we are mainly interested in this smoke variable. Okay, and so I'm going to do, in my first stage, I'm going to regress on smoke all of the other variables. So income, age, female, pregnant, education, unemployed. And so this is my instrumental variable, whether or not the person is unemployed. And then in my second stage, what I'm going to do is I'm going to add to my BMI data a prediction of my first stage model. And so now, if I run these two guys, and I take a look at my data, I should have an unemployed column, and then you have a predicted unemployed. Okay, this is probably not the best example because unemployed is a categorical variable, but we're kind of treating it as linear. This is actually a topic that we'll talk about in the next lecture. We haven't gotten to categorical or discrete response variables in your y, but we'll get there next lecture. But so kind of just take this as it is for now. And so instead, when we go into our, this is the predicted for smoke, not for unemployed, which is still a categorical variable. So instead of plugging in smoke as a variable in the second stage, I'm going to plug in the predicted smoke. So here in my second stage, I'm regressing BMI on income, age, whether or not they're female, whether or not they're pregnant, how much education they have, and then my predicted variable from the first stage. And so we can run this. And we can look at these results. So you may find that the results are now quite different from your ordinary least square example. And here, so if I look specifically at smoking, which is the thing that we care the most about, here, if you're a smoker, then it increases by 0.29 on average, your BMI, whereas here we say that if that the causal relationship between smoking and BMI is that actually your BMI will increase by about, say 18 or so for, if you start smoking on average. All that having been said, right, we've kind of identified that this is not necessarily a good example of an instrument because your instrument is maybe related to other variables and is being confounded itself. And so unemployment would be an example of probably a bad instrument or an unjustifiable instrument. So now let's try this with the cigarette tax. So it's exactly the same. Let me add in the summary here. So this is our first stage, and here is our second stage. In the first stage, we regress on the variable of interest, smoking, and we include our instrument here. Again, this isn't, this isn't something where it's not necessarily a super robust check of your instrument. When I look at the summary of the first stage, ideally you'd want all of these to be sort of statistically insignificant, except for your cigarette tax. And that's not always the case, because you may sometimes just randomly have correlations, right, between your instrumental variable and some of your explanatory variables. This isn't really a common way of measuring the validity of an instrument. It's usually more done qualitatively. I always kind of worry about seeing this pop up, but I guess for some reason people don't really consider it that strong of a metric of determining the validity of an instrument. One thing that you will note, though, is that so we qualitatively have pretty good reason to justify cigarette tax being a good instrument, right? Because because we're fairly confident that it's basically unrelated to a lot of these things, and so oh, sorry, I misspoke. It's not that these are significant, which is actually okay, right? Because this is related to smoking, not to cigarette tax. It's the correlation between your variables and your cigarette tax. Yeah, I'm hallucinating a little bit. So don't worry about these being significant in your first stage. It's more about if you run a correlation matrix with your cigarette tax, if the level of correlation between cigarette tax and a lot of these can sometimes randomly be relatively high. And like, that's one of the things that isn't considered necessarily a good measure of the validity of the instrument for some reason. But it can be worrying when the correlations are high. So sorry, I misspoke. Don't worry about these. So for one of the things you'll notice for the cigarette tax is that it's not very statistically significant, the relationship between cigarette tax and smoking. And so what that means is that even though we have a good qualitative justification for it being a good instrument, it's also a weak instrument, which is to say that the relationship between people actually smoking and like the size of the cigarette tax just doesn't seem to be that robust. And so we're going to see how that's going to affect our second stage. Ruh-roh. I didn't run all of this. Okay. So here, when we do this regression, we can see that the effect of smoking is now really quite high. So it's 137 BMI on average. So if you start smoking, what this model tells you is that that's going to, on average, lead to 137 BMI higher, which is a really large amount. So all else equal, if you start smoking, that's the effect that this model is describing. Oftentimes, when you have weak instruments, it's just going to say that the effect is not significant, and we do see that here. And in addition, sometimes that can affect a lot of the other outcomes as well. And so that's where some of the uncertainty about the effect propagates through your model. And so this is one of the drawbacks that I was mentioning. Okay. So this is, I think it's clearest for students to be able to see the model sort of written out this way, because it's really, or I think it's a lot easier to see what's going on, right, with the first stage and second stage, how you're treating the instruments, and then how using the predictions in your second stage. But of course, there are packages out there which will do this for you. Oh, shoot. Okay, there's one really important point that I glossed over, which is that the standard errors in your second stage, if you do it manually like this, are not correct. Okay, so these values are incorrect, and there is some statistical reason behind why that is, and so you can actually recalibrate the standard errors to get the right values. That process is a little bit more tedious. So right now, actually, we can't believe any of these probabilities, and so I'm actually not going to go into detail about how to calculate those standard errors. I'm just going to show in the built-in packages that do two-stage least squares regression, those will obviously calculate the standard errors correctly. The main reason why I'm showing it manually like this is so that you have sort of clear in your mind what's going on with the first stage, second stage, but don't trust in the size of the standard errors and the corresponding levels of significance. Okay, there's a question. So we don't need to make sure each variable is significant in both stages. No, you probably do want to make sure, in particular, the significance of your variable of interest, so the smoking variable. Yeah, so one of the issues is that oftentimes it doesn't become statistically significant because of the uncertainty in the first stage, which can often be an issue where you come up with a good instrument, but it's not statistically significant. But let me do the example with the built-in package, so we can actually see what the right standard errors are. So the package, one of the packages that does two-stage least squares is called AER, which apparently I don't have installed. So let me do that real quick. There's no package called AER. Oh, wait, no, that was from the first one. Okay, while it's loading, I'll just throw this in. So the syntax for it, instead of linear model, it's called IVReg, right, which stands for instrumental variable regression. And so you regress BMI on all of your variables, and then for the variable that you're interested in having instrumented, or your variable of interest, which is smoke, you have this extra syntax with a vertical line, and then indicating what variables to include. So it kind of wraps everything into one sort of line of code, but it's indicating sort of two levels of regression. Okay, so I can run that model, and we can take a look. So in the manual case, the standard errors are going to be smaller than they should be, because of the way that you need to modify the standard errors for predicted values as you introduce these predicted values into your regression. Okay. And so here we're actually getting the right ones, and you can see the significance is even sort of smaller. Okay, there's a question just to make sure. So the estimate is valid, but not for the other stuff to the right. Yeah, so if you're doing it manually, that's right. So here, this is 137.2 essentially, and the standard error is 118 or 1,180. So really big standard error. Whereas, okay, sorry, let me just do it like this. Whereas here, okay, it's 100. So in the one we calculated manually, it's 137.2, which is the same as the estimate. So the estimates themselves should be exactly the same and correct, but the standard errors are going to be way, way smaller. So this is just 98 as opposed to 1,180. Yeah. Also, you'll note the R squareds. You're getting some weird values here. I don't know why they even bother posting these. It's actually the R squared is going to look really weird because you're using the predicted values. So you there's actually a way you can do an R squared for instrumental variables in two-stage least squares, and I'm kind of surprised that they haven't implemented it here, because these are obviously not right, because your R squared should always be between 0 and 1. I kind of just noticed that the package doesn't do the modified version. Okay, so I guess you can't trust the R squares even in the built-in package. Okay. So that kind of wraps up discussion about thinking about causal relationships and how to measure that and doing it in practice with instrumental variables. The most common way is to do this two-stage least squares thing. There are definitely more complex treatments of instrumental variables and ways to address some of the nuances and drawbacks that I've discussed today. But this is mainly to give at least an introduction and overview to a pretty different approach for understanding regression relationships. So I will say that I think a lot of this class is more focused on the predictive aspect of it. And yeah, I think if we back up for a second and we think about at a high level what these models are trying to do, there's a lot of ongoing and age-old arguments about whether you should be or how important the predictive element of getting Y's are, or in other words, your response variable, in the context of building causal models, right? And so I think that a lot of folks put a lot of emphasis into this whole idea of being really robust in choosing a good instrument, getting a valid instrument, demonstrating that you've controlled for all of its relationships with the confounding variables. And they put a lot less emphasis on the predictive aspect. In other words, like if I were to estimate my Ys out of sample and compare them to actual data, like how accurate would I do? And I guess you just don't see that much of that happening in models that are focused in causality. And to a degree, I can kind of see why, right? A lot of the instrumental variables and putting in these procedures to do these two-stage least squares introduces a lot more uncertainty. And so you end up oftentimes with stuff like this, where you have no variables of significance. But I think that even if you are doing more causal-based methods, that you shouldn't forget about what it means for your relationship with Y. Because I think at the end of the day, even if you get a good causal relationship, but you can't say anything about, or you can't say anything accurate about your model outcomes, then like what was the, I guess, what was kind of the point of getting the causal relationship, right? If I can't really describe how my Y will change. Okay, and so this bit of it, I'm sure lots of folks would probably disagree with me, but it's something to keep in mind, right? How well your model estimates your Y. So I would encourage that if you do this kind of stuff, if you're more sort of ingrained in the econ world, don't dismiss don't dismiss the strength of being able to accurately predict your Ys. Okay, I guess that concludes our lecture for today. Yeah, sorry that office hours again was canceled. I will try and work something into my schedule this week, and I'll make an announcement on Canvas about having makeup office hours since the internet was down. And okay, since I'll also note that I'm gonna just repeat what I said at the beginning, because I see that there's a couple more people participating who have joined in since my announcement at the beginning of lecture, which is that I post notes about what I've lectured on every day in the files, and so if you've missed something, if it's gone too quickly, or if your notes aren't clear, you can refer to those. Those notes have been sort of worked on over the last couple of years and compiled up, and so I'm fairly happy with them. And they're sort of extra material that is complementary to the lectures. And so if you need any secondary sources about what we've been covering, you can look at those notes, which are, and again, they're all posted on Canvas, and I post them within a couple days of the lecture. Okay, so we'll end here for today, and we'll do the same thing. I'll stick around a couple minutes for any questions that folks may have.